Hello and welcome to another NGen Math 6 lesson by eMathInstruction. My name is Kirk Weiler and today we're going to be doing Unit 3, Lesson 1, the first lesson in our unit in Math 6 on decimals. Now, our first lesson is on the base 10 number system, and you've been working obviously with the base 10 number system your entire life. That's what we deal with, right? And we have a base 10 number system for a very simple reason, mathematically or historically, because we've got 10 fingers. All right. I mean, had we lived on another planet where there were like 3 fingers on each one of our hands, we would then have a base 6 number system in all likelihood. There's even some evidence historically that some cultures used a base 20 system because they used not just their fingers, but also their toes. All right. And so today what we're going to be doing is we're going to be reviewing some basics about the base 10 number system, all right, but at a higher level, right, than where you were at like in kindergarten and first grade, obviously. And the important property that the number 10 has in our base number system, right? So all the 9 digits, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 are important, but the number 10 is especially important because we are in a base 10 number system. So let's get right into it and do a little bit of review about our important number system and how it behaves. All right, here we go. The number system based on powers of 10. So that's the deal, right? Our entire number system, from tens to hundreds to thousands to 10,000s to millions, etc., all of that are based on powers of 10, meaning products that just involve the number 10. In exercise number 1, we're going to do the following. Write each of the following products as a power of 10 and then give its result. All right, so very simple, especially letter A. Let's do this together. 10 times 1, right, is simply 10 to the first, which is 10. That's a little bit maybe of a silly one. 10 times 10, when we talk about powers of 10, that is what we say 10 to the second power. And of course, as we all know, that's 100, right? 10 times 10 times 10, that's the same as 10 to the third power, and that is 1,000. Really, really important. 10 times 10 times 10 times 10, that's 10 to the fourth power, and that's 10,000. Now, of course, what you probably notice, and maybe I should put the comma in the right place there, otherwise it's a bit confusing. What you might notice is, of course, in each case, as we multiply by yet another power of 10, we go from a 1 and a 0 to a 1, 0, 0 to 1, 0, 0, 0 to 1, 0, 0, 0, 0, right? And that's because we've got this system that's based on the number 10, or more appropriately, based on 10 digits. 10 digits. All right, let's keep going. Now, probably one of the first things that you ever did with the base 10 number system is the idea of taking a number that's just written normally, like 2,475, and writing it in what's known as its expanded form. All right, let's take a look at exercise number 2. Write the following numbers in their expanded form. Represent them using powers of 10 exponents. The first is done as an example. All right, so like literally, you've gotten to probably a point where when you see something like 2,475, you just kind of look at it that way and you don't think about it very much more deeply than that. And yet, what 2,475 is 2 times 1,000, because we've got 2 thousands, 4 times 100, because we have 4 100s, 7 times 10, because we have 7 tens in that number 70, and then just 5 ones, right? So that's 2 times 10 to the third, plus 4 times 10 to the second, plus 7 times 10 to the first, plus 5, right? So it's super duper easy. Let me show you how to do it in letter B, right? When we have 5,762, that's just 5 thousands plus 7 times 100 plus 6 times 10 plus 2. That's actually a pretty good way of leaving it, but in terms of powers of 10, that would be 5 times 10 to the third plus 7 times 10 to the second plus 6 times 10 to the first plus 2. And we want to remember that. We want to remember this idea that when we have a number like this, it's not simply a 6 sitting beside a 7, sitting beside a 6, sitting beside a 2, right? It's literally 5 1,000s, 7 100s, 6 10s, and then another 2. Why don't you go ahead and do the same thing for 16,703. All right. Well, there's the way we read the number, and then there's sort of like what we have in terms of powers of 10. So we definitely have 16 1,000s. But in terms of powers of 10, what we really have is we have 1 10,000, 6 1,000s, 7 100s. We have absolutely 0 10s. And then we have 3. So in terms of writing it with exponents, we'd have 1 times 10 to the, whoops, not 10 to the 5th, times 10 to the 4th. You can always figure that out by how many zeros there are. 6 times 10 to the 3rd, 7 times 10 to the 2nd, 0 times 10 to the 1st, and then 3. Right? 1 10,000, 6 1,000s, 7 100s, 0 10s, and 1 3. All right? The expanded form of the number. And it really helps us to kind of crystallize the fact that when we have a number, what we're keeping track of is how many of particular powers of 10 we have, right? We have 1 10 to the 4th, 6 10 to the 3rds, 7 10 to the 2nd, 0 10 to the 1st, 3 left over. Let's keep going on to see what we can think about given this expanded to the form of a number. Understanding place value. Place value is simply when we have a digit, 0 through 9, right? There are only 10 digits, 0, 1, 2, 3, all the way up to 9. When we have it at a particular place in a number, right, then how much is that worth? Exercise number 3. Fill in the missing blanks below. All right, so in each one of these particular, missing blank problems, we're going to write in a number. Maybe it's a fraction, maybe it's a whole number that makes these statements true. What I'd like you to do is pause the video now and see if you can figure out what to fill in for A through D. You can also take a look at letter E, but we'll talk about that one together once we go through A, B, C, and D. All right, well, this is simple enough, right? 30 is going to be equal to what times 3? Well, that's pretty simple. 30 is equal to 10 times 3. 7,000 is equal to what times 700? Well, that's just 10. 10 times 700 is 7,000. Now, letter C, this is way more challenging. 2 is equal to what times 20? Well, here it's not a whole number, right? But it is a fraction. 2 is equal to 1/10 times 20, right? Literally, 1/10 times 20 is the same as 20 divided by 10. So it's equal to 2. Same thing on letter D. 50 is equal to 1/10 times 500. Now, what this leads us to is a very simple fact about our place number system, which is that a digit represents 10 times its value one place to the right. And again, understand what I mean by this. If we had something like 335, right, this represents 30, but this represents 10 times 30, or 300, right? So a digit always represents 10 times as much as it would one place to the right, and likewise, one place to the right and 1/10 times its value one place to the left. In other words, this 30 represents only 1/10 of the 300, all right? And again, you've known this for quite some time, but it also allows us to say, well, if I multiply this particular one by 10, I get this. Or if I multiply this particular one by 1/10, I go back to that one. All right? They're very different, right? These two 3's represent two very different things, 30 versus 300. So where we want to get with this then is a very fundamental idea about multiplying by powers of 10 and dividing by powers of 10. Let's look at that in the next exercise. Exercise number 4. Explain why 10 times 243 is 2,430 by using the distributive property and the expanded form of the number 243. So for years, you've learned, and I certainly hope and expect you to know and use this, that when you multiply a number by 10, you just sort of stick a 0 at the end of it. And if I multiplied a number by 100, I'd stick a couple zeros at the end of it, etc. We'll get into the dividing in just a bit. But why is that? Why? Why would we just take 243 and put a 0 at the end? Well, let's take a look at that, right? We can do 10 times 243 by looking at 10 times 200 plus 40 plus 3, right? Now, that, when we distribute it through, right, since we're multiplying by 10, right, since we're multiplying by 10, we literally want to move each one of these digits 1 to the left, because we are getting now a number that is 10 times as great as each one of them. So that 200 becomes a 2,000. I don't really need the parentheses anymore. That 40 becomes a 400. And that 3 becomes a 30. And then, of course, that is 2,430. The idea is very simple, right? When we multiply by 10, each one of these digits gets 10 times as large and therefore moves, if you will, 1 to the left. All right? That has the effect then of making it into 2,430. Now, at the end of the day, if you're saying to yourself, look, I just know that when I multiply 243 by 10, I slap a 0 at the end, that's fine, all right? Because we want you to know that. But this is why it works, okay? Let's keep moving on. Right, so products and quotients involving powers of 10. It's really this simple, right? When we multiply by powers of 10, right, whole number powers of 10, we're going to move the decimal place in our number that many digits to the right, all right? And when we divide by powers of 10, we're going to move our decimal place that many units to the left. So let's take a look at exercise 5. Find each of the following products or quotients. Awesome. So let's do some of these together. Right, I have 10 times 57. The idea is 57 is the same as 57.0. By multiplying it by 10, what I literally am doing is moving that decimal place 1 point to the right and getting 570. Now, I would expect that the vast majority of you would just write down 570. But since we're getting into a unit with decimals, it's good to think about how multiplying by powers of 10 will affect the decimal point. Same thing with 10 times 60, right? That is literally going to be 10 times 60.0, which means we're going to move that decimal 1 place to the right so that everything gets bigger by a factor of 10, and we have 600. Now, on the other hand, if we multiply by 100, which is 10 to the second, 10 times 10, we're going to move that decimal place 2 places. So, whereas if we had 36.000, etc., we're now going to move it 2 places to the right, we will now have 3,600. And if we multiply by 1,000, we move that decimal place 3 to the right, giving me 457,000. All right, multiplying by powers of 10, so simple. Now, when we divide by powers of 10, we move that decimal place in the opposite direction. So in letter E, when we have 650 divided by 10, We then think about that decimal point being right here, and because we divide by a single power of 10, we now have 65.0, or just 65. Likewise, if we have 7,400 divided by 10, we move that decimal place 1 unit to the left, and we get 740. If, on the other hand, we divide by 100 or by 1,000, we'll move those decimals 2 places to the left in terms of 100, and 3 places to the left in terms of 1,000. So, for something like 120,000 divided by 100, we'd go 1, 2, and we'd be left with 1,200. Or, without those extra zeros tacked on, just like that. Likewise, 2,456,000 divided by 1,000, 1, 2, 3, we would just have 2,456. All right. Now again, this only works when we divide or multiply by powers of 10. If we divided and multiplied by powers of 3 or 7 or 9 or whatever, oh, it just get ugly, you know. But 10, right, because of the way digits work in our system, since every digit is 10 times the digit that's immediately to the right of it, when we multiply by 10, all those digits just simply shift to the right, and then we add zeros on, or all those digits shift to the left, and we have to move the decimal place inward and make the number smaller. Let's keep going with this. Few more problems. Decimals and powers of 10. Literally, in the word decimal is DEC. DEC stands for 10. Decimals, though, now have to do with tenths, hundredths, thousandths, 10,000ths, etc. So let's do some review of some basic decimal ideas. Exercise number 6. Represent each of the following decimals in terms of fractions involving base 10 denominators. All right, so simple enough. 0.1 by definition is 1/10. All right, it is the fraction 1/10. It is what I get if I take 1 unit and I divide it into 10 equal pieces. One of those equal pieces is 1/10, right? On the other hand, if there's a 3 there, that's simply 3 times 1/10, or 3/10. All right. Now keep in mind, right, as I sort of move in this direction, my fundamental unit gets smaller, right? So if I take 1/10 and I divide it into 10 pieces, each one of those then is 1/100th, and that's what I have here. And likewise, instead of having a 1 there, if I have a 7 there, I don't have 1/100th, I have 7/100ths. And this pattern just keeps going, right? Now if I move the decimal one more place this way, right, then I have this divided by 10, and if I take 1/100th and I divide it into 10 equal pieces, they're getting very small now, right? Then I have 1/1000th. And likewise, if I have 4 of those pieces, I have 4 1,000ths. And we just keep going. So one more place out, instead of having 1/1000th, I have 1/10,000th. Commas are optional. And likewise, if I have a 5 in that place, I have 5 10,000ths. It's amazingly important to understand the connection between decimals and fractions whose denominators, the number on the bottom, are powers of 10, because it is the way these numbers are defined. It's just a different way of showing them without having to have the fractions there. And the reason we don't have to have the fractions there is because all their denominators are 10, or 100, or 1,000, or 10,000, or the next one would be 100,000, the next one would be 1,000,000, etc., etc. And as that denominator gets bigger each time by a power of 10, our little piece becomes smaller. 1/10th, 1/100th, 1/1000th, etc. Let's keep going. One last problem. We can now write out a number that includes decimals, also in its expanded form. Let's take a look at exercise number 7. Write each of the following numbers in their expanded form. The first is done as an example. So in other words, we want to go back to this idea of really understanding what a number represents. So 28.34 is literally 2 tens, 8 ones, 3 1/10ths, and 4 1/100ths. I'd like you to do the same for letter B and letter C. Pause the video now. All right, let's do it. So in this case, again, it's all about the number 10, right? So what we are going to have here is we're going to have 3 hundreds, right? We're going to have 1 10. We're going to have 5 ones. We're going to have 6 1/10ths. And we're going to have 2 1/100ths, right? Now, it really wouldn't be incorrect if you wrote this as 6 divided by 10 or 6 over 10 and 2 over 100. But kind of like what we did here, we really want to say, oh yeah, I have 3 of these hundreds, 1 of these tens, 5 of these ones, 6 of these 1/10ths, and 2 of these 1/100ths. Let's do letter C. In this case, we start with tens. We've got 5 tens for 50. We've got 8 ones, and I'm going to throw that in. 8 times 1, I'm going to throw that in as well, right? Then we have, whoops, where'd that plus go? We have 3 tenths. We have 9 hundredths. And we even have 5 thousandths. And again, each one of these things is 1/10 of the one that came before it. Same thing here, right? 10 is 1/10 of 100. 1 is 1/10 of 10. 1/10 is 1/10 of 1. Duh. And 100 is 1/10 of 1/10. Each time we're either increasing by a factor of 10 or decreasing by a factor of 10, i.e. dividing by 10. All of this is very important before we move on in the next few lessons to add and subtract decimals, multiply decimals, and finally to divide decimals. Let's summarize. Our entire number system, including the addition of decimals, are based on powers of 10, right? With a digit 1 unit to the right, sorry, 1 unit to the left being 10 times what it was 1 unit to the right, and 1/10 if we go the other way around. Because of this, right, all sorts of different things happen in our number system, including nice things, like when we multiply a number by 10, it moves the decimal place to the right, and when we divide by powers of 10, it moves the decimal place to the left. We're going to need that quite a bit in upcoming lessons. For now, I want to just thank you for joining me for another NGen Math 6 lesson by eMathInstruction. My name is Kirk Weiler, and until next time, keep thinking and keep solving problems.